So in this video we will state and prove the chain rule of differentiation with full analytical rigor. So firstly we'll state the chain rule then, so setup first. So we're going to have two functions f and g that are both going to be real valued functions defined on closed intervals over the real line. So the domain of f is the closed interval AB and the domain of g is the closed interval CD. And then we're going to create a third function which is going to be the composite of f with g, which means first do g, then do f. The domain of this function is going to be the domain of the function g, so it's going to be the interval from c to d, and it's going to map those elements onto the real numbers, so it's going to be real valued. And of course, in order for this composite to be defined, it needs to be the case that this mapping g maps its entire domain onto something that is inside the domain of the function f. If it were to map an element here onto something outside of this domain, then of course we wouldn't know what to then map that onto under f. So I've written that here, that the image, which I've written big G, of the set, which is the entire domain of the function g, so the interval CD, must be contained within the domain of f, which is the interval AB. So the chain rule then, written out in full, says that if g is differentiable at some point p within its domain, so p is an element of the interval CD, and f is differentiable at whatever that point p is mapped onto by the function g, so g of p, then you can conclude that the composite function f composed with g is differentiable at the point p, which will be within its domain, and it will have derivative equal to the derivative of f at the point g of p, which we know exists, times the derivative of g at the point p, which we know exists. So I've drawn a little picture here to help clarify this. So here is our domain of the function g, the interval CD. Here is our point p inside that domain, and then the function g maps it onto g of p, which we know has to be inside the domain of f, so it has to be somewhere inside this interval AB. And then the function f maps it onto f of g of p, here, somewhere in the real line. And therefore the overall composite function takes you from p to f of g of p here. And we're saying if the function g is differentiable at the point p, we'll call its derivative g prime at p. And if the function f is differentiable at g of p, we'll call its derivative f prime at g of p, then you can overall conclude that the composite function f composed with g will be differentiable at the point p, and its derivative is going to equal these two multiplied together, so f prime at g of p times g prime of p. So let's now prove this famous calculus result. Now, the proof of this is a little bit tricky, even though when you set out to prove this, it looks as though it's going to be simple. However, very quickly, a problem raises its ugly head, and I'm going to show you that. So if the composite function f composed with g is going to be differentiable at the point p, it means that this limit must exist, the limit as t approaches p of the difference quotient for the composite function, which is f of g of t minus f of g of p divided by t minus p. So our aim is to show, using these assumptions, that this exists and that it has value equal to this. So the tempting but unfortunately fallible thing to do, and indeed the thing that many calculus textbooks do when they're trying to explain why the chain rule is true, is to manipulate this algebraically thus and turn it into this thing in green. So we've got the limit as t approaches p. Now this bit has remained the same. This is just f of g of t minus f of g of p. That's that bit. This bit has also remained the same. We've got t minus p. But then these two are new. We've multiplied and divided by the same thing. So here we've got multiplied by g of t minus g of p, and then we've divided also by g of t minus g of p, and then we've split it up into two separate fractions that are then multiplied together. The next move the calculus textbooks make is they split this up thus into two separate limits, and they say if these two limits exist, then by the algebra of limits, multiplying them together yields this, therefore this thing will exist as long as these two exist, and it will have value this one times this one. Then they say, well, look at these two limits. Let's look at this one firstly, because this one's beautiful. Limit as t approaches p of g of t minus g of p over t minus p. We know the function g is differentiable at the point p, so this limit is going to exist, and it's just going to have value g prime at p. Now this one, well, this one's a little bit more difficult, but if we were a calculus textbook, we wouldn't look at it too deeply, and our argument would go something like this. We know the function g is continuous at the point P because it's differentiable at the point P, and differentiability implies continuity. Therefore, as t approaches P, g of t here is going to get closer and closer to g of P. So, you can imagine, if you like, substituting this with a u here, and u is approaching this value g of P, and then you're taking the limit as u approaches g of P, you then have the difference quotient for the function f at the point g of P. So because we know the function f is differentiable at that point g of P, that limit is therefore going to exist, and it's going to have value f prime at g of P. That would be their argument, quaderat demonstrandum. This one is equal to this one is equal to this, therefore this is equal to this, therefore this is equal to this. Therefore, our composite function is differentiable at the point P, and its derivative is this. So unfortunately, this argument is flawed. We can fix it, but as it stands, it is flawed. And let me show you where the flaw first comes in. It comes in with this algebraic manipulation here. How do you know that this thing that you're dividing through by here is not equal to 0? How do you know that g of t is not equal to g of P for some t around P? What if this function g was the constant function that mapped all the points on the domain here onto just one value? Then for all t inside the domain CD, it would be the case that g of t was equal to g of P. So this is a problem. Now, even if you'd let me get away with this algebraic manipulation, let's say I did it sneakily and quickly and you hadn't noticed that there was a flaw with that argument, I wouldn't have overall got away with this proof. The same problem would have reared its ugly head and stopped me at this point. You see, I, unlike the calculus textbooks, would have tried to properly prove this limit is equal to f prime at g of P to you. And when you try and do that, the same problem as is stopping you from doing this rears its ugly head again and stops you being able to prove that this limit is equal to this. So no, this is not okay. Put a great big cross through all of this. We need to go back up to the blue bit and start again. So let's fix this then. Before we do begin, let me just give you a warning. There are different ways that you can prove the chain rule correctly. The way that I am going to show you, the fix for this incorrect proof that we've just been through, is beautiful, it's simple, it's elegant, it's quick, but it is not so intuitive. Other ways that we could do this are more intuitive, but they actually end up taking longer and they are more arduous, and in my opinion they are actually harder, but they are more intuitive. As I say, the proof that I'm going to show you is beautiful, simple, elegant, but when I start by writing down this new magic function that's going to save us and get rid of all these problems, you're going to say, how on earth did you come up with that? How on earth was I supposed to intuitively concoct this? I say to you, bear with it. It will become apparent how this function fixes everything, and it is a beautifully quick and simple proof. So after that warning, here is the magic function that is going to save us, and gosh, doesn't it look complicated. So we're calling it the function h. It is going to be defined from the interval CD, which remember was the domain of the function g, the first one in the composite function, and it's going to map onto the real line. And the rule is going to be given thus. It's a piecewise rule. So for some t inside our domain, h of t is given by this thing here if g of t is not equal to g of P. So this is f of g of t minus f of g of P over g of t minus g of P. Now you should recognize that. That is this part from our dodgy proof over here. So now this h of t is basically going to be the better version of that in this manipulation. That's what we're going to do. We're going to substitute it in place of that. And note, h of t is going to do better than this because it's only going to be equal to this when g of t is not equal to g of P, i.e. when this is actually defined. So for all t inside this interval, if g of t is not equal to g of P, then this thing will be defined and you're going to make this the value of h at that t. for values of t in the domain where g of t is equal to g of p, then we cannot define h of t to be equal to this because it's not defined. Instead, we're going to set it to be equal to this, f prime at g of p. So that's a constant value, so any t inside this domain that is being mapped by g onto the same thing as the point p is going to be mapped to a constant value, which is f prime at g of p. Indeed, the point p itself will be mapped onto this by the function h. So if you ask what is h of p, it does not satisfy this criterion, it satisfies this criterion. G of p is equal to g of p, therefore h of p is going to be mapped onto this constant. So the natural question that should be going through your head is why? Why do I care about this function h of t? Why would you do this to me? Why would you define this? Well, at the moment, I'm afraid all I can say is you can't stop me defining this h of t, and carry on watching and you will see how this is going to save and sort out everything. So here comes the first hint of genius of this. So remember, we are trying to prove this limit exists. The limit as t approaches p of f of g of t minus f of g of p over t minus p, and that it equals the chain rule formula. Now, I claim that this thing inside the limit here is the same thing as this over here, and therefore that this limit is the same as this limit. So the limit as t approaches p of h of t times this thing here, g of t minus g of p over t minus p. And now let me just slide across so that we have the green one in view here. This h of t, therefore, is taking the place of what we have here. This thing here has been carried over to here, and now we're replacing this bit that had flaws, remember, with this h of t, and I claim that it is now the fixed version of h of t that gets rid of this problem that you might be dividing through by 0. So how does this work? Well, firstly, consider a t where g of t is not equal to g of p. H of t in that case is this thing, so you can put this in place for h of t here, and you'll see that g of t minus g of p's will cancel, and you'll end up with f of g of t minus f of g of p over t minus p, i.e. you'll end up with the exact thing that I claim it's equal to. Now consider a point where g of t is equal to g of p. In that case, h of t is going to equal this, but it doesn't actually matter, because look at what's going to happen here. You'll have g of p now, because we're saying g of t is the same thing as g of p. So you'll have g of p minus g of p, i.e. you'll get 0 over t minus p. So that will still be 0 overall, times this thing, which is just a constant. So overall, the answer will be 0 in this case. Now look up here. When g of t is equal to g of p, put in g of p here, you'll get f of g of p minus f of g of p over t minus p. Again, that'll be 0 over something, 0 overall. So this quotient, this difference quotient, is equal to 0 in the case that g of t is equal to g of p, and the thing over here is also going to equal 0 in the case that g of t is equal to g of p. Otherwise, when g of t is not equal to g of p, it reduces to the same difference quotient back again, because it's this multiplied with this. So for all t in this domain, this, h of t times this, is an equivalent function exactly the same as this. Therefore, the limit as t approaches p of this difference quotient is the same thing as the limit as t approaches p of h of t times this difference quotient. Now time for some algebra of limits. If these two limits, the limit as t approaches p of h of t and the limit as t approaches p of g of t minus g of p over t minus p, if they both exist, then you'll be able to combine them together using the algebra of limits to yield this limit, and you'll be able to conclude that this limit exists. And then I've just hopefully convinced you that this limit is the same as this limit, so we'll know that this limit overall exists. Now this limit we've seen already, no problems at all. G is differentiable at the point p, so this limit does exist, and it's equal to g prime at p. So really the big question is, does this limit exist? The limit as t approaches p of h of t. So if this function h of t has a limit as t approaches p, then we're in business. And of course it is going to have a limit as t approaches p, because I have built it in such a way that it will. In particular, why did I choose this constant? You probably understand this part of the function now, so that it cancels and overall gives this difference quotient. But in these cases where g of t is equal to g of p, we know this difference quotient over here is going to be 0. So actually, this one being 0 does the job. I could have set h of t equal to whatever constant I liked for these values of t, where g of t is equal to g of p. And this bit of genius here, where I can replace this with h of t times this, would still have applied. So why did I choose that constant? Well, it's because picking that constant is going to mean that this function does have a limit as t approaches p. Whereas if you choose any other constant apart from that, this wouldn't work. So now all that remains to do then is show formally that the limit as t approaches p of h of t does exist, and indeed it's going to equal this value f prime at g of p, so that overall this times this yields the chain rule, because of course this is g prime at p. So how are we going to prove this then, that the limit as t approaches p of h of t is equal to this value f prime at g of p? Well, to help us, I've started to draw a picture here. So here is our domain for the function h, which is the interval cd. Here is our point p. The point p is then being mapped onto this value f prime of g of p. We know that because p satisfies this criterion here. G of p is equal to g of p, therefore h of p is this value. And now what we want to show is that the limit as t approaches p of h of t is also equal to this value. So what we need to show then is that for any epsilon interval around this value f prime of g of p, so here is our epsilon interval in aquamarine here, so f prime at g of p minus epsilon to f prime of g of p plus epsilon, that there will exist a delta interval around p, here it is in yellow, p minus delta to p plus delta, such that all the points inside there are mapped into this epsilon interval here. And we don't need to actually worry about subtracting the centerpiece of the interval here from that requirement, because we know p is always going to be mapped inside this interval because it's being mapped onto the centerpiece of the interval. So actually we can just leave it as the simpler criterion that the entire interval needs to be mapped into here. So the first observation is very simple. If you consider any radius interval you like around the point p, and you look at the points inside that interval that satisfy this criteria, now there might only be one of them. It might just be the point p that satisfies this criteria. However, there might, in general, be other points that satisfy this criteria. So points inside that interval, so points t, that are mapped onto by the function g, the same thing as g of p. They, of course, are going to be mapped by this function h according to this line, this rule here. They're going to be mapped onto this constant f prime of g of p, i.e. they're going to be mapped onto the centerpiece of our interval here. So they therefore are guaranteed to be inside whatever epsilon interval you like. So basically, inside this delta interval, you do not need to worry about the points that are being mapped according to this rule, the points that obey this criterion. They are guaranteed to be inside this epsilon interval. We just need to worry about the points that don't obey this criterion, that follow this criterion instead. So this is now going to require a bit more work. So to reiterate what we need to show that there exists a delta interval around this point P such that for those points inside that delta interval that obey this criterion, i.e. g of t is not equal to g of p, and are therefore mapped by h according to this rule, that the value that they're mapped onto is going to be inside this epsilon interval. So the value they're being mapped onto is given by this difference quotient here. So we are going to need here to use the fact that f is assumed to be differentiable at the point g of p. So I've added onto our picture here. Here is the domain of the function f, so the interval ab. Inside that interval is the point g of p. The function f, by initial assumption, is differentiable at the point g of p. Therefore, the limit as u approaches g of p of f of u minus f at g of p over u minus g of p, this limit is guaranteed to exist, and it's going to be equal to f prime at g of p. So that's just the limit as u approaches g of p of the difference quotient for the function f at g of p. So crucially, this value f prime at g of p is showing up again here. So I've drawn on to the picture something that's going to be highly helpful, which is this difference quotient function. So this function takes any u in our domain from a to b, apart from the point g of p itself, and maps it onto this difference quotient, f of u minus f of g of p over u minus g of p. And of course, you can't put u is equal to g of p in here because you'll get division by 0. Now, I could have drawn a separate real line for it to be mapping into over here. However, it's going to be far more helpful for our intuition to have it mapping into this same real line over here. So the fact that the limit as u approaches g of p of this difference quotient function here equals f prime at g of p, this value here, that means that for all epsilon intervals that you put around f prime of g of p, and we'll use this same epsilon interval here, I can find you a delta interval around g of p, and we'll call it delta bar so it's not confused with this delta over here, this interval g of p minus delta bar to g of p plus delta bar, such that for all of those points inside that interval apart from the centerpiece itself, and it is important to remove the centerpiece because this function, this difference quotient, isn't actually defined for the centerpiece. So all of those points in that interval apart from the centerpiece, they're going to be mapped by this difference quotient inside the epsilon interval, i.e. the value of their difference quotient is somewhere inside this epsilon interval around f prime of g of p. Now, for all the t over here that satisfy this criterion, i.e. g of t is not equal to g of p, and are mapped by h according to this rule, you can now view this mapping in two parts. You can view it as firstly map them according to the function g, so take them onto g of t, and then put them through this function. So if you substitute for u g of t here, you'll notice this will become f of g of t minus f of g of p over g of t minus g of p, i.e. it becomes this thing. So for these t's that are mapped according to this rule, we can split it into a composite of two parts. Firstly do g, and then apply this difference quotient function. We can use this splitting it into these two parts to help us now conclude that we can find this delta interval such that these points mapped according to this rule are all going to be inside this epsilon interval if they're inside this delta interval. And this is how the function g is going to be continuous at the point p, because it's differentiable at the point p, and differentiability implies continuity. That means we know that the limit as t approaches p of g of t is equal to g of p, which means that we can take any epsilon interval around g of p and we can use our delta bar interval here as our epsilon. And I can find you a delta interval around p such that all the points inside that interval are mapped into that epsilon, in this case delta bar interval, around g of p. So that's how I'm going to find my delta interval. Find it so that all the points inside here are mapped into this delta bar interval around g of p. And then I know that all these points inside this delta bar interval are going to be mapped into the epsilon interval around f prime of g of p by this difference quotient function, but the composite of those two functions overall makes the function h, and therefore h is mapping all these points into that epsilon interval. So the only concern you might have is what if some of the points inside this delta interval around p are being mapped onto g of p itself, because it's only the points inside this delta bar interval that aren't the centerpiece that are guaranteed to be mapped inside this epsilon interval around f prime of g of p. But hopefully you've spotted the genius of this. We were only using this to prove it for these points, the points which we said were not being mapped onto g of p, the t's where g of t was not g of p. The other points we'd already proven it for. So to summarize then, for your epsilon interval around f prime of g of p, you can find a delta bar interval around g of p, such that all the points inside that delta bar interval, apart from g of p itself, are mapped by this difference quotient function into the epsilon interval around f prime of g of p. Because of the continuity of the function g, I can then find you a delta interval around p such that all the points inside that interval are mapped into this delta bar interval around g of p. I claim that that delta interval is then the magic delta interval such that all of the points inside that interval under this function h are mapped into this epsilon interval around f prime of g of p. To see that, we split it into two cases, the points inside the delta interval that are mapped according to this criterion and the points inside the delta interval that are mapped according to this criterion. Let's start with these ones. These ones are easy. The ones where g of t is equal to g of p, they are mapped straight away onto f prime of g of p, i.e. the bang center of this interval, so they are immediately assured to be in there. The other ones that are mapped according to this rule, you can view this rule as being split up into two parts. Firstly do g, and then perform this difference quotient. Now we know that everything inside this delta interval around p is going to be mapped by g into this delta bar interval around g of p, and for the points in this delta interval that satisfy this criterion, we know that they're not going to be mapped onto g of p, so they're mapped actually into the deleted interval, the interval without g of p in the centre. We then know that everything inside this deleted delta bar interval around g of p is mapped by this difference quotient function into the epsilon interval around f prime of g of p. Therefore, all of these starting points here that satisfy this criterion are guaranteed when you go through these two functions to end up inside that epsilon interval. So bingo, we've done it. We've shown that for a general epsilon interval, we can find a delta interval such that all the points inside it are mapped into that epsilon interval. So we have proven, therefore, that the limit as t approaches p of our function h of t does exist, and it is equal to f prime at g of p. And note how crucial it was to have this constant set equal to the value of that limit, i.e. f prime of g of p, so that you could conclude that all the points in the delta interval that satisfy this criterion are, of course, mapped into the epsilon interval around that value. So overall then, this thing is equivalent to this thing. This and this, these two limits exist, therefore you can combine them together using the algebra of limits. It gives this, therefore this is going to exist, and it's going to be equal to the value of whatever this is times whatever the value of this is. This is clearly g prime at p, and we've just shown that this is f prime of g of p. Therefore, the composite function f composed with g is differentiable at the point p, and it has derivative equal to this. And with that, we will finish. Thank you for watching.